Hello, everyone. Oh god, that's such a generic intro. Hi, fuckers, and welcome to mathematics again. So there was a few mistakes with the last one, and now I'm realizing a few more mistakes. So we're gonna go over it now. Just so you know, and just to remind everyone, I am not perfect. I do not give all the correct answers. I might be wrong. Okay, so take it with a grain of salt. Okay. Okay, we're going to be starting on. I wonder if I can actually point to this time. Yes, we're going to be starting up here. Hopefully the screen sharing software will work. This is the 0006 paper. It includes all the same questions as 00010. Nope, 0010. But it adds one extra question, notably number 1. If you can sort of see my cursor over here. It adds this, essentially. And all the rest of the questions are just here and then will come up later. But essentially we're just going to go off this paper for now. Okay? So, let's start with the first one. So, what it's asking us for is the solution here, okay? Now, if you remember from inverting a matrix, actually, if this is true, and we can get a solution here, then another thing has to be true. X is also equal to the inverse times that, okay? So, we need to figure out, if this inverse exists, then we can get a value, essentially. If it doesn't, well, it doesn't. So let's figure out, does this matrix have an inverse? Now, can we do that? Well, determinants, mostly. If a determinant of A is equal to 0, then it is seen as singular, and therefore we cannot get an invert matrix, essentially. Because remember, when we do inverting a matrix, we have 1 over the determinant. So if the determinant is 0, then no luck, right? However, if it's not 0, then we can. It's non-singular, and we can differentiate it. So we need to find the determinant. So let's try this. We have the matrix 2, 4, 1, 3, 5, 0, 5, 13, 7. Now I want to reduce the first column first. So I want to take away this 3 and this 5. It's going to go to, essentially, 2, 0, 0. Now to remove these, I need to minus, essentially, I think 1.5 lots. Yeah, so 2 times 1.5 will make 3. So I'm going to essentially subtract 1.5 lots of 1. For 5 it'll be the same. I'm going to subtract 2.5 lots of 1. And of course the top row stays the same. So, subtracting 1.5 lots, obviously the 3 cancels out. 4 times 1.5 makes 6, and subtracting that makes negative 1. Then doing this for 1, it's 1.5, subtract that, it's negative 1.5. I'm going to write 3 over 2 because it makes it a little easier for me. Pardon me. Sorry if that was a bit too loud. So, we've got next 5, which cancels out. 4 times the 2.5, minusing from that, makes 3. And then we've got the 2.5 times the 1, which is, well, 7 minus 2.5, which will be 4.5, which many of you might recognize as 9 over 2. Now you can quite clearly see here that this second row has a lot of similarity with the third row. As a matter of fact, it's directly a factor of it. So that means we can just sort of cancel it out. Now this is indicating something quite annoying to us. Okay? If we can cancel this row out, and we can, if we times this by minus 3, then essentially it becomes the same thing, so it just cancels out, almost. But you remember that when finding the determinant, we find the product of all diagonal entries after we've reduced it, yeah? What's here? Well, it's 0, right? So, if the determinant of A is 2 times negative 1 times 0, it's going to be 0. So, non-invertible, this matrix we can't inverse, so it has no solutions to the above equation, okay? Because we cannot get this inverse, okay? We cannot multiply it by b, and we cannot get a value of x. So this equation essentially has no solutions. Okay, let's move on to the rank. Well, actually, rank could be quite easily found out with this. So you see here, the rank is essentially how many sort of subgroups of independent, what is it? Yeah, of independent vectors that you can sort of get. So in this case here, we have sort of 2 groups, okay? We have these 2 up here, and we've got this one, okay? as this bottom one is just 0, 0, 0, so it's its own sort of vector because you can't get anything else out of it. And then we've got this one up here, which we've already got something out of it, right? We've got essentially a rank of 2 here. So the rank here is 2 because we've got 2 groups. This one and this one. If you want more detail on rank, I'd recommend you look at the book. It has a bit more nuanced explanations than I do. Okay. Let's move on to number 2. This is for everyone now, so pay attention. Number 2. So we need to find the determinant. Essentially, we're going to do the same thing. Remember, keep that third in front. We're not going to include it just yet. We're going to mix it in at the end. It's like a bloody cooking recipe. Reserve your third for the end of the recipe, and it'll make a lovely garnish. Anyways, here we go. Alright. So essentially we want to reduce rows here. We're going to essentially, because we've got, see, you've got 2 and 2 here, and we've got 1 in the top. So we're going to essentially minus 2 lots of the top equation, which I represent as minus 2 lots of first equation. Okay. From that, we're essentially going to keep that 1/3 in front. We've got 1, 0, 0, fairly obviously. Given that we are minusing 2 lots of that, so we're going to be minusing minus 4, which gives us 3. And we're, hold on, let me write that in. And then minusing minus 4, and again, plus 4 gives us 6. Then we're going to be minusing 4, which gives us negative 6. And minusing 4 from this gives us negative 3. Okay? So we've reduced the x1 row, now we go for x2. So see here, you've only got this sort of 6 to take out. And simply put, it's just 2 times the second equation. So we're going to go from there. Keep that third in front. And we will have 1, minus 2, 2, 0, 3, negative 6, and we're minusing 2 from it. So it's going to be 0, 0, and then negative 2. So it's going to be adding 12, I believe. So that gives us 9. Okay, then, and only then, do we multiply every value by a third. But really, the only values we care about are the ones on the diagonal. So what we get is essentially this matrix. Okay, and all we care about are those ones on the diagonal. Hold on, let me add in the zeros. So we're going to multiply them, okay? So the determinant of, is A? It's A. The determinant of A is going to equal 1/3 times 1 times 3, which gives us 1, quite simply. So that's the determinant. Okay. Now, orthogonality is a quite different thing. Hold on, I'm going to cough again. Excuse me. Orthogonality is quite a different thing. Orthogonality states that A multiplied by A to the power of t, where A to the power of t is transpose, okay, is the transpose of the matrix, equals the identity matrix, okay? So essentially this is what it's going to look like. We've got our normal matrix here. I'm just going to write out again, just to make sure you guys have all got it, and then we're going to transpose it. Now transposing essentially means taking the columns and changing them to rows. So, also remember to keep that third in front. We're going to do 1, 2, 2 across, minus 2, minus 1, 2, minus 2, minus 1, 2, 2, minus 2, 1, 2, minus 2, 1. There we go. Now we've just got to multiply these out. I will spare you guys the long multiplication because that's a bit annoying and you guys probably don't want to see that. But essentially, just take my word for it, when it comes out to 999 with all the zeros. So it's 9s on the diagonals with zeros. And as we can see here, because we times the thirds from the fronts as well, we get a 9th, okay? Which eventually resolves to the identity matrix. 1 on the diagonals, we get that. You guys should be able to do the multiplication step by yourselves. I'm not going to take you through that because it takes a little too long. But essentially that is it. We've showed that the regular matrix times the transpose makes an identity matrix. Okay, that's number 2. Or number 1 if you're really calling it 10. Okay, now this is the one which we had a bit of trouble with. In fact, I had a bit of trouble with. Apologies. I figured out that I was wrong to this with the first lecture this week, just about proportional rates. Let's just quickly zoom in on that. I wonder if I can probably get this. So it's saying, consider the form for the production function of an economy. We've got that. Where Q, KL denote output, capital, labour and time respectively. If KL only depend on T, find an expression. Okay? So this was fine. God, it's fine. Essentially, the expression for this is essentially multivariate chain rule, or just regular chain rule if you want to say it. Say we have some function I'm going to call big F, which is a function of the variables x1, x2, and x3. Now, let's say that, let's just continue onwards, because it could be literally anything. Now let's say that x1, x2, x3, all of these are something like a function of t, okay? Because that's normally what you kind of get. So these are all functions of t, essentially. What we essentially do is that we say, okay, say I want to differentiate the big F with respect to t, okay? What I'm essentially going to do is I am going to get the partial derivative of f to one of the variables, let's do x1 because that's the first, and then I'm going to get the regular derivative of x1 to t, okay? And this is generally how we do it. We also continue this for all other variables, so we would do the partial derivative of f with respect to x2, and then the regular derivative, and essentially we would continue on and on and on and on and on, okay? For our example, we've got q is a function of k, l, and t. Remember the t, okay? We're going to come back to that. So what we're essentially going to do is we're going to do, well, dq dt, as the question requires. And remember, the question also requires we put it in terms of partial derivatives of the production function and the time derivatives of k and l. So these are going to have to be included. So we're going to start with k. Okay, as k is a function of t, we put the partial derivative of q relative to k, and then we put the time derivative of k. We're going to then repeat this for L. And then for t, something interesting happens. So you'd expect to just do the usual thing, but hold on, what's this at the end? dt over dt would inherently be equal to each other, so we're just going to cancel that out. Plus, if we did dt to dt, it would literally just be nothing, so wouldn't be much point to it. Okay, so now we've got our little thing here. Now, this is the area where I fucked up, so just take notice. Look at what it says here. Now suppose that k and l have constant proportionate rates of growth. Okay, I'm going to highlight that, constant proportionate rates of growth. This is where I messed up. Is someone screaming? Apparently so. Anyways, constant proportionate rates of growth essentially says that the time derivative multiplied by the function over 1, so 1 over k times dk over dt is equal to that rate of growth. The question says m and n respectively. So for k, it's going to be m. Oh, it's going to be m. And then for l, it's going to be n. Which leads us to dk of dt equals km, and dl over dt equals ln. Pardon me. Last time, I just thought it was m and n. That was my mistake. I apologise for that. Let's move on to the actual calculation. So, we've got our formula here, so we're going to write it in terms of this formula. We've got the partial derivative, no, not the partial derivative, the real derivative of q to t is going to be, well, first of all, let's look here. The partial derivative of q to k, okay? So, our function, let me write that function at the bottom. We've got q is equal to ERT, k to the power of alpha, L to the power of beta, okay? If we're doing a partial derivative to k, then we're only going to derive relative to k, okay? Which means its power is going to go back here and minus by 1 by the power rule. So, for partial derivative of q relative to k, that is essentially going to be equal to ERT alpha, k alpha minus 1, and L beta. Lambda, not lambda, L is going to have the same sort of thing, so I'll just redo this for that. It's going to have ERT, and the regular k to the power of alpha, but it's going to put the beta at the front. So we've got that. If we want to do partial derivative to t as well, we might as well do this, because then we'd have everything together. And that's just going to derive relative to t. The only t here is that. So it's essentially deriving an e to the power of x function, which you guys know how to do. We're just going to slap that r at the front, and it's just the normal function. So let's combine it. Okay. So we have this function here, e to the power of rt alpha k alpha minus 1 L beta multiplied by, let's look back here, dk dt, which we already said was km. Okay, so km plus the Labour version. I wonder if you guys can see all of this. The Labour version, which is going to be e to the power of rt, k to the power of a, beta L times beta, to the power of beta minus 1. And this is going to be ln plus, well, remember this is just alone, so we just add the E-R-E-R-T, and then the regular stuff. Okay. Now we can see that all of these have in common the e to the rt, the k to the alpha, and the l to the beta. Okay. Obviously, we can separate these minus ones, though. Okay. I should probably move this down here just to make it a little easier to look at. So, what I'm essentially going to do is out of the first term, I'm going to take out e to the rt, k to the alpha, and L to the beta. I'm going to take these out of all terms. For the top one, we leave alpha and k to the power of minus 1. So we have alpha and k to the power of minus 1. And also remember, k on the outside and m. We're also going to do the same thing for the next one. So we have L, which also has the same issue. It's going to leave beta and L to the power of negative 1 outwards. So it's going to beta L to the power of negative 1. And then it's also timesing by L and N. Finally, we leave out the R in the final one. Okay. Now, obviously some of you probably noticed that k to the power of minus 1 times k to the power of 1 here is just going to cancel. So we just cancel all these out. And essentially what we're left with is this. E to the power of rt, k to the power of a, L to the power of beta, the original function, multiplied by alpha m plus beta n plus r. This is the solution. You could also simplify it as q. Oh, again, it's that. Oh, I've made it look like a fraction. Just ignore that. You could also simplify it as q alpha m plus beta n plus r, which I have. Okay, that's number 2 now. Or number 3, or whatever. Now moving on to number 9. Let me just pause as I scroll. Voila! Here it is. Okay, now I'm aware that a lot of people had trouble on this because it's a bit vague, but essentially I'm going to go through everything here. So, first of all, it asks you to define the terms linear combination, linear dependence, and linear independence as applied to vectors. I'm not going to bother writing it out, so I'm just going to get my notes and show you guys. Do you guys see? Oh, dear Lord, that is difficult. So essentially, I'm going to read it out. And hopefully you guys will hear. Linear combination. Okay, linear combination, when we apply linear operations to 2 or more vectors to obtain another vector. You guys should know this, I'm pretty sure. Linear dependence. This applies to a set of vectors where one vector in the set is a linear combination of the others. Fairly simple. Linear independence is essentially the opposite of dependence. And no vectors can be expressed as a linear combination of others. There you go. Okay, hopefully you guys should know that. Now, suppose A, B, and C are 3 vectors in Rn, okay? So Rn states a basis set. It's what we're going to mention later, but let's just go over this. So we want to show that they are linearly dependent only if there exist scalars of alpha, beta, and gamma, not all 0, such that alpha plus A plus beta plus B plus gamma plus C equals 0. Now, I believe this was mentioned in notes, which I'm just going to quickly pull up, so bear with me. Okay, here I am on literally the first lecture notes. This essentially has the solution to the problem. Suppose A, B, and C are linearly dependent. You guys might take a picture of this. What is all happening here? Oh well. Yeah, linear dependent. What is he writing? Suppose for... What is happening? Suppose for determinant that a linear... Oh yeah, okay, so we're supposing essentially that A can be expressed as a combination of beta of B and C. So we're going to say it can be expressed as beta plus times B plus gamma times C. Okay, suppose that it could be expressed like this. Okay, so essentially what this means also is that we can also express it like this. Alpha is plus beta B plus gamma C, okay, which equals 0. We could also express it like this. So we have alpha, beta, and gamma. Okay, oh, we could also have like... so we have, but not x equals 1 minus 1. Oh, this is very confusing, pardon me. I could barely read this. Hopefully you guys can read it a little easier. Okay? So, essentially... Okay. Let's assume, just quickly, that x does not equal 0 in this case. So we're going to... I think this is what it says. Yeah. So if you can sort of see around this area, okay, this is the main proof. So we've got the alpha plus A, beta plus B, gamma C equals 0, essentially. And suppose that alpha does not equal 0. Okay, so this A vector here isn't 0. Then, essentially, the A vector, multiplied by alpha, is going to be equal to negative beta over alpha, B, negative gamma over alpha, C, which equal to, well, nothing, really. So therefore, and A is a linear combination of B and C. Okay, so we've basically roundabout done it again. So if this is true, then it follows that this is true. So it's a really roundabout way of doing it. I'm not entirely sure. There is a way of proving this with echelon form, which is that if we reduce this matrix and it becomes echelon type 1 or 3, then essentially the vectors are independent, and if it's 2 or 4, it's independent. Oh, it is, no, sorry, wrong way around. If it's 1 or 3, then if it's 1 or 3, then it's independent. If it's 2 or 4, it's dependent. Essentially. So this sort of just says what it is. But this is the official proof, as you can sort of see here. If anyone can actually read this, power to you. But I think this is the proof. So suppose there is, so you've got this, which is what we had here. And then, therefore, A is got to be a linear combination of B and C, essentially, for when alpha doesn't equal 0. So there's got to be something. So by that logic, they should be linearly dependent, essentially, as long as something isn't just 0. Okay, I know that's a bit confusing, so sorry about that. I can't really offer much help on it. It's kind of confusing me too. But let's move on. So, we have, for the next one, we need to show that these are linearly independent. So, essentially, if they're linearly independent, then this has to be true. The alpha A plus beta B plus gamma C, it has to always equal 0. So let's try this, okay? So we have 1, 0, 0, which we're timesing by alpha, so we'll get alpha 0, 0. We've got beta times the 1, 1, which makes beta, beta. And then we've got gamma times, and it's 1 for everything. And if this is independent, essentially, wait, hold on. If it's independent, essentially that means that, it's going to be, hold on, let me just double check here. One moment, let me just pause and clarify. If it's linearly independent, then it means essentially that this has a solution of 3 zeros. So, this is our proof for linear independence. Does this have any other solution other than just 3 zeros? Well, no. As you can sort of see here, the gamma equals 0 immediately. And if gamma equals 0, then beta's got to equal 0. And if beta and gamma equal 0, then alpha equals 0. So if alpha, beta, and gamma all equal 0, then it's independent, essentially. So we literally cannot come up with anything that works here, because literally gamma down here is taking it all out, because we know gamma has to equal 0. So this all follows through. At least that's what I got. Okay. Let's just move on. Now we want to see if any 3 vector can be expressed as a combination. So let's try this again. Okay, we have our vector as before, and we're going to multiply them by the scalars, alpha, beta, and gamma again. And we want to make it equal to any vector we want. So I'm going to say it is equal to the values a, b, and c, where a, b, and c are anything I want, okay? Given that gamma is equal to c here, then, well, b, or beta, really, beta is going to be equal to gamma, which is what, no, it's, hold on, beta plus gamma, pardon me, equals b. As we know gamma already equals c, then we've got beta plus c equals b. Therefore, beta is equal to b minus c, essentially. Then, inevitably, we've got at the top here, we've got alpha plus beta plus gamma equals a. As, hold on, let me get a bit more space for this. As alpha plus, so beta we've already established as b minus c, plus gamma, which we've already established as c, equals a. Then, essentially, we've got b minus c plus c, cancels it out. We're left with alpha plus b equals a. And alpha is equal to a minus b. So, essentially, we have 3 values that we can set our scalars at to achieve any vector, essentially. So we can essentially get any vector we want. There's no limitations here. If we have c, then we can change the value of b to make it beta. If we have the value of b, we can change it to make it alpha with a. Essentially, we can do anything we want. So, then it says what to do when it could be generalized. Now, I'm going to bring out the book for this, just so everyone knows where the actual thing is for it. Pardon me. It is at 11.1. Here it is. Now, this might be hard to see, so I'm just going to... I wonder if I can actually move the camera towards it. If you guys can just sort of see that. Oh, that is tricky to see. Okay. Yeah. Hold on, let's just see this. On problems on chapter 11, at the bottom of the page, it says a set of 3 vectors with properties a and b. As you can see up here, a and b are the 2 properties that we've just stated. Properties a and b, hold on, let me move it, is called a basis of R3. I know that's a bit blurry to see because I probably didn't focus the camera correctly, but that's essentially what it's called. Oh dear, does that work? Hooray! So, what we call them is that we now know that V1, V2, and V3 are a basis, some might call basis set, a basis of R3. Essentially, this means that they can create every vector that is the size 1 by 3, but they can't make each other, essentially. That's what it means, okay? They're independent, and they can't create each other, but they can create all others, okay? Essentially, they can't help anyone else other than other people. Okay, I think that is it. Now, hopefully, that is better, okay? Sorry that this had to be uploaded, like, later. I was quite busy, but hopefully you guys are happy with that. I've gone over it again now. I'm pretty sure that this is all right. Sorry about the start of 3, this sort of, this proof here. You can find it in lecture notes 1, as you can sort of see up here. But yeah, that's all from me. Okay, hope you guys have a nice evening, and see you later.